Hey again, everyone. You ever get a dumb idea stuck in your head? I do, pretty often. This was probably one of them, but you can let me know how stupid this whole thing is down in the comments. If you've used generative models to create images, or even looked at more than a handful of AI-generated images, you've probably figured out two of the major limitations of most methods. That is, generating realistic hands and fingers, and generating text. Text can be produced with other methods, like directly generating images from a font file and superimposing it on the generated image, or through inpainting or ControlNet, and similar methods can be done with hands. However, that's all a little complicated. But if you've generated a number of images, you've probably seen that occasionally the output will have very clearly rendered and logically placed text. Or that sometimes it will have related text that wasn't prompted, such as a coffee mug with the word coffee on it, or the word hot. So I got to thinking about how to guide the model to produce text.
Hey, look, you know how you're always talking about how you can simulate all that stuff on your computer? You know?
Think of it. The brain of a dead man, waiting to live again in a body I made with my own hands.
I could train a new model with Dreambooth using captioned images, but I don't really have the resources for that. But a new model isn't really portable, and there are some really great Dreambooth models out there. Or I could train some type of LoRA. The benefits of a LoRA being that it's portable between models, and it trains fewer parameters, requiring less memory to train, and may converge on good results faster than a Dreambooth trained model. I ran through a lot of tests with this. I almost nailed it with Stable Diffusion 1.5, but I kept hitting a wall. Stable Diffusion 1.5 is prone to repeating patterns. I think that has something to do with the original image sizes that were used during training. When generating text, it would often get stuck on a letter and keep repeating it. To compensate for that, I think supplying and training on images less than 512 by 512 might help a little. But I got really tired of looking at variations of the same output images over and over with Stable Diffusion 1.5, so I finally threw in the towel. Trying to do this with XL is probably easier, but it does take more resources. So running each test takes me quite a bit longer, and I haven't quite got it down perfectly yet. However, I thought it'd be worth outlining what I did here in case anyone wants to follow along and refine the process and train a better adapter. In terms of LoRa adapter types, the only one that is really usable for this in my environment is the IA3 adapter. These are small, train quickly, and seem to perform as well or better than other adapter types. For the optimizer, I'm using Prodigy again, similar to the video I put up recently. I've tried other self-adjusting optimizers like D-Adaption, but Prodigy seems to work better for me. I find that it tends to get stuck less, if that makes any sense. The downside of Prodigy is that it converges a bit slower, so it may take more epochs to train. And for the scheduler, I've tried linear, constant, and cosine. I found that using cosine annealing seems to help keep the training from getting stuck. To do that, I think you need to supply the command line argument in the advanced options of the Koya GUI if you're using that. I'm going to spend a while going over the dataset here because I think this is going to have a bigger impact on the outcome than any of the training parameters. I had mediocre results using crudely generated training data, and much better results when using carefully selected images following a general scheme for captioning. I've put together a dataset with a handful of classes of images that contain text. Video game box art scans were cropped to 768 by 768 to contain the title and as little other text as possible, to try to keep the captions as clean and simple as I can. I used the Bing Image Scraper Python package to gather magazine and movie cover scans, and then deduplicated the images with the Dupe Guru tool for Windows. Then I cropped the images to focus on as few text strings as I could. I went over the Image Scraper and Dupe Guru in a previous video if you're interested in that, and I'll link that down below. Using the Bing Image Scraper, I also gathered some photos of neon signs. These were difficult to assemble because there wasn't a great source for high-resolution photos of actual neon signs. I tried to avoid modern neon lookalikes and computer-generated images, and I captioned the text in each segment of the sign separately. Some time ago, I also came across a scraped dataset of t-shirt images on Kaggle. If I can find the original source, I'll link to it down below. I selected some clear images from the dataset and cropped and captioned them. Similar to the neon signs, if the text was in the same font, I captioned it together, and if they were in different fonts, I captioned each segment separately. This part of the dataset took a long time to put together, but I think it's important to have real images as part of this training dataset. I've tried this using only synthetic data and the results were promising in that I was getting clear text output, but it looked as if it was superimposed on the image rather than part of the image. While I have a good assortment of images, I really don't think it's going to be adequate to try to refine the text generation of Stable Diffusion. The shapes of the letters are going to be a small subset of all possible variations of those shapes amongst various fonts, if that makes any sense. There's a lot of cursive text and block lettering, but not a lot in between. And the shapes of letters on neon signs are going to look odd, so I think it would help if there were other images with text that had a similar shape to assist in the shape to letter token associations in the model. Rather than spend dozens more hours captioning images, I'm going to generate another set of images using a wide variety of fonts. For this, I'll be using Python and the Pillow library with help from some code segments I found searching online that were a bit more efficient than my own. I'll quickly go over the script here, which I'll link down in the description if you want to customize it for your own use. And the script is written for Pillow 9.5 at best, I think. Some of the functions are deprecated in Pillow 10, so you'll have to downgrade or keep a separate cond environment for this to work. Up at the top of the script, the width and height set the dimension of the output images. The phrase list is a set of sentences or words to generate. I'm using 2 pangrams, which are sentences that contain every letter. The quick brown fox jumps over the lazy dog, and the 5 boxing wizards jump quickly. There are others, but these are a couple of the shortest that happen to make grammatical sense. And I can remember them. Supply an input directory of TrueType font files and set an output directory for the images and caption files. Just note, if you're trying to juggle font files in Windows, you may have trouble deleting them, as Windows seems to try to generate a font file preview and then locks the file. You may need to use a font manager if you're trying to juggle a directory of hundreds to thousands of font files, so I'll link to a good font manager down in the description. I've tried doing this with only black or white backgrounds, and I think having either extreme may train worse than having an assortment of colors. I've selected some name colors that are subdued, ones that would normally be the color of things that have text on them, like shirts or paper or walls or whatnot. This will loop through the provided fonts and phrases using a font size within a random provided range and fill it with one of the colors from the earlier list selected at random. The size of the font's characters are averaged to fit a text box slightly smaller than the image size. If the image spills over the line length, it's wrapped to a new line. This doesn't take into account line height, so with tall fonts, your text may be stacked too tightly. The text is drawn on the image using a random color. You'll probably want to delete garish color combinations or text that's difficult to see after generating a batch of images. The font base name and the phrase are used in the output file name, and the text is captioned with English text and then the phrase in quotation marks. The image is rotated some amount between -45 and 45 degrees, and the empty space is filled with background color from earlier, and then it's saved to a PNG alongside the caption. After the images are generated, I look through them and delete anything with ugly color combinations or where the font and background color are too similar. I've also deleted text that's too small to be legible or too large to fit the image, as well as images where the font just doesn't look clear enough to be a good example to the model. I'm going to be using these generated images in 2 training scenarios. When they're being used as training images, I'm going to keep the generated and trimmed set as it is. And when they're being used as regularization images, I've added some additional captioned images of various celebrities just because it was easy to find curated collections of images to skim through. Now I'll go over some of the more interesting training runs and talk about the changes to the dataset and parameters. I've had the training script generate some sample images every 100 steps, which is far more than I'd normally do, but I want to be able to show the progression for the video. This first session is using a dataset of single words rather than the pangrams as sentences, simply because I'd started training this before I'd worked out the image generation script. This was using the Prodigy optimizer with cosine annealing. This dataset also contains a few character image sets, so I can see how the text training affects training with characters and styles. Characters as in characters from media like TV shows and movies, not characters from a page. I've reused some old captioning image sets of Alice from Alice in Wonderland, Meg Griffin from Family Guy, and Velma from Scooby-Doo. This will let me see if the individual character styles can be kept separate with this, or if they're going to bleed together into a colorful mess. The test images generated are 768 by 768 and generated using the same seed. I let this first run train for a long time, but the training slowed to a crawl. I set a fixed number of epochs, 200 for this, but it was probably a bit too high. I've also set the optimizer arguments decouple equals true, weight decay 0.1, I've left the D coefficient as 1, set use bias correction to true, safeguard warmup to true, and I'm using the min SNR gamma of 5. I've also set debiased estimation loss to true, which may end up interfering with the min SNR gamma setting. It seems like after doing some reading that it may be best to use debiased estimation loss with the min SNR gamma and noise offsets disabled. While the images were mostly coherent, there were still incorrect letters when I stopped training. Prodigy can reportedly take a long time to train, but if this takes dozens more hours, trying additional training runs in the future isn't really going to work on my PC. I need to speed things up by using a more efficient noise augmentation method or using a smaller dataset. With the second run, I'm using images generated with the pangram sentences and a more carefully curated, slightly smaller dataset. I'm using the pangram generated images as regularization images here, and the other captioned images containing text as the training images. I've also removed the character images to speed things up, so I'm using only the pangram sentences as regularization images. Well, this session's quite a bit better. More uniform training that seems to progress in the right direction, however there are still some misplaced characters. Disabling the min SNR gamma reduced the required step count, and I think I can get away with far less than 200 epochs, especially with the larger datasets. For future runs, I've reduced the epoch count down to 50 maximum, and to speed things up, I generate sample images every 500 steps instead of every 100. I only let this train for something like 17 epochs, but it seems to be working alright. I'm going to cut the middle section from this video because I'm not sure there's much to be gained by going over the other training runs. I've done a lot of them to test various parameters and to try to get a balance between being able to render something resembling text and having an adapter too strong that obscures the output from the rest of the model. I'll summarize things as best as I can here. There was little benefit using the batch of generated images with text as regularization images. Things seem to perform better by adding them to the dataset. However, when added to the dataset, they would often crowd out the rest of the training data. By this I mean biasing the output towards gray backgrounds and very simple scenes. The synthetic dataset seems to need to be balanced with real-world captioned images. The other large positive change I made midway through testing was changing the captioning strategy. The script shown earlier in the video generated text in quotation marks. I found it worked better to use 2 sets of 3 asterisks rather than quotation marks. I've tried other optimizer and scheduler combinations, including shiny new ones like Adafactor and Dadaption. Nothing seemed to perform any better than Prodigy and introduced new quirks that I would have to contend with. With Prodigy, I've had reasonable results by setting the D0 value to 0.01. This is the initial learning rate, and Prodigy seems to perform best with a high initial learning rate. Using the D coefficient less than 1 seems to keep training more stable than using 1 or greater. Lowering beta 2 to 0.91 may be too extreme, but values smaller than 0.99 seem to help things train a bit more uniformly. Using betas 0.9 and 0.99 seems to give erratic output until very late into training. But ultimately, a lot of the behavior is probably going to be highly dataset dependent. I've loaded the adapter up into the Auto1111 Stable Diffusion WebUI and generated some images to see how the output may be affected. This seems to be a more reliable method than just typing in something like cup with the word hot or sign with text gas. Text seems to be placed in logical areas of the image more frequently than when not using the adapter. With some images, it's difficult to force text to be generated. Rather than text, the adapter seems to try to place logos or emblems on things, as it did here with the Ninja Bear. Different descriptors can be applied to the text, sometimes resulting in characters looking like they've been rendered with Kai's power tools for Photoshop 3.0 or whatever it was that we were all pirating back in the day. Whether or not this project is useful at all, well, I have no idea. Actually using the adapter is fiddly, and I'm not saying this is a reliable method at all. But with some more refined training, it might work a little bit better. It's just a silly thing I was fiddling around with. More competent and creative hands may be able to do better with this, but I'll leave that up to you. I'll link the image generation script and one of the test IA3 adapters that I've trained here if anyone wants to try it out, and see if you'll get anything resembling text out of it. That's all for now, and thanks for watching.